All right, so as we've been doing all the past reviews, I'm just going to go ahead and read the questions out, and then I want y'all to tell me the answer. And then, as I stated, if anything doesn't make sense for you, just go ahead and ask, and I will clarify anything that you may have questions about. Okay. So, first one, in a bivariate table, the marginals are the what?
B.
B, so the row and column totals. So that's probably just something you need to memorize. Just remember that it's just a different name. It's just a different definition. So, but marginals and totals are the same thing. Good. All right, so let's take a look at number 2. For a test of the difference between two sample means, it is easier to reject the null hypothesis if what? So we have a 2-sample t-test. It is easier to reject the null hypothesis if what?
I'm going to say all of the above.
Okay, good. So the answer is all the above. So one thing you just need to memorize is that when the samples are large rather than small, this is the case for a lot of hypothesis testing procedures. It's easier to reject the null. 2, when the alpha is equal to 0.05 versus 0.01, it's easier to reject the null. And one of the reasons why that is because the 0.05 alpha level is the easiest alpha level to reject at. Okay, now 0.01 is harder. And then 0.001 alpha level is the hardest alpha level to reject the null at. So because 0.05 is the easiest one, obviously that's the case as well. And a one-tailed test is used rather than a two-tailed test. Now, can anybody remind me why it is the case that a two-tailed test is harder to reject the null than a one-tailed test? Does anybody remember why that's the case? All right, so hopefully you all remember when we were talking about the t-test, and we were talking about the t-test. The first example that we gave was the mean wage of African Americans being less than the mean wage of all Americans. So we wrote the hypothesis, less than. So we did a left-tail test. So we did a one-tail test. And if you all remember, the hypothesized population mean was 28,985. We pulled a sample mean of 24,100, and then the p-value associated with that sample mean was 0.0183. Okay. Now, that's if you do a one-tail test. If you all remember from that lecture, if you were to do a two-tail test, you're equally as interested in the probability below the mean as you are above the mean. So you'd be doing a 0.0183 on this side and 0.0183 on this side. So what you're doing when you're doing a two-tail test is that you're doubling your p-value. Now, obviously, if you double your p-value, it's going to be harder to get it below your alpha level, because what you want to do is with your p-value, you want your p-value to be either at or below your alpha level, okay? So let's just say that your p-value is 0.0183 for a one-tail test. If you make it a two-tail test, it becomes 0.0366. Now at the 0.05 alpha level, in that situation, you still be below, but again, if you have your p-value in a one-tailed test is like 0.03, well, if it was a two-tailed test, it'd be 0.06. So that's why it's easier to reject with a one-tailed test than a two-tailed test. All right. Three, a t-test is used when what? T-test is used when what?
C.
No. You can use large samples.
Is it A?
Good, so it's A. It's when the standard error is estimated from the sample data. Now, if you can estimate the standard error, then you're going to use the T. But if you have the standard error, then you would use the Z and you'd use the normal distribution. So if you were to calculate the Z, you could do the sample mean minus the population mean divided by the standard error of the mean. The way you get the standard error of the mean is equal to the population standard deviation divided by the square root of n. Now the T equal to the sample mean minus the population mean divided by the estimated standard error of the mean. And then you would use this, estimated standard error when you are estimating the standard error from the sample standard deviation. Okay, so this is the sample standard deviation. And this will be the population standard deviation. Okay, so yeah, so in this situation, you'd be using the T instead of the Z when you're estimating the standard error from the sample standard deviation. Okay, and that's kind of what you need to know about, using the T statistic or the T obtained versus the Z statistic of the normal distribution. And obviously in this situation, we'd be using the T distribution as opposed to the normal distribution as well. Anybody have any questions about this? Okay. Number 4, when a t-test is used to test whether there's a difference between two sample means, which formula to use for the t depends on whether what?
The population variance are unknown or known.
The answer is sample variances are equal or unequal. Now, what does this mean? Okay, so yeah, because I kind of feel like this question is a little confusing to tell you the truth. So if y'all remember from that lecture, we were talking about two sample t-tests, right? So two samples, and then the top part of the calculating the t for a two sample t-test is really easy. You just take the mean of the first sample and you subtract it by the mean of the second sample. So the top part's easy. But the bottom part, finding the estimated standard error for a two sample t-test, that can be kind of complex. So there's two equations to get this bottom part. One is if the variances are equal, then you use this equation to find this bottom part, okay? But if the variances are unequal, then you use this equation to find this bottom part. So having said that, the T is, or the type of equation that you use to find the T is dependent on whether or not the variances are equal or unequal. And when the textbook talks about equal versus unequal, they mean equal if one is not more than double that of the other. So let's just say you calculate the variance of one sample and the variance is like 5, and then you calculate the variance of the second sample and the variance is 15, well, then you know that the second sample is more than double that of the other. But if the variance of the first sample is 5 and the variance of the second sample is 6, well, then that would at that point still be considered equal, okay? All right, now the degrees of freedom for a t-test of the difference between two sample means is equal to n of the first sample plus the n of the second sample minus 2, which are the two restrictions, which are the two samples, for is except for. So this is the degrees of freedom except for what?
Unequal variance?
Good. Okay, good. So it is unequal variances. So again, just like the bottom part of this equation changes depending on whether or not you have equal versus unequal variances, the degrees of freedom changes depending on whether or not you have equal versus unequal variances. So if the variances are equal, then it's pretty simple. It's right here. Okay, your degrees of freedom is n for the first sample plus the n of the second sample minus 2. But if the variances are up here unequal, then the degrees of freedom formula is this, which don't worry about it on the exam. You're not going to have to calculate it. Just understand that if you do have, differences in variances or unequal variances, then you might need to know that, the degrees of freedom formula isn't this simple, it's this. But the vast majority of time, the degrees of freedom formula is going to be this, okay? Okay, for a t-test with 40 degrees of freedom, the critical value needed to reject the null hypothesis using a one-tailed test and an alpha of 0.05 will be what? Okay, now this isn't something that you can recall from memory. So what I would suggest you do is, if you don't have the book, well, if you do have the book, just go ahead and bookmark the table. So go ahead and bookmark the T table, the normal distribution, stuff like that. Maybe put a little post-it note there so that's easy to find. But since you're using an ebook or an e-reader, you have it as a PDF, the textbook as a PDF, it's kind of hard, in my opinion, to like scroll through all that stuff, when you're on your computer. So I would just print out the tables, okay? So what you need the T table for this. You're going to go ahead and jump over here. T table looks something like this. This isn't the whole T table. It's shortened for this PowerPoint. So what you do is you'd first find the degrees of freedom. So it said 40 degrees of freedom. So 40 degrees of freedom. So you first find the 40 degrees of freedom. We find it here, okay? Now it also told us the one-tailed test at the 0.05 alpha level. So we come up here, we see one-tailed test. Obviously below is for the two-tailed test. So we see a one-tailed test at the 0.05 alpha level. So we come down here, 40 degrees of freedom, 1.684. So as long as our T obtained is either 1.684 or above this number, which is the critical value, we can reject the null hypothesis. So that is, again, the answer. So we need to be greater than or equal to 1.684. Then we get to that critical value and we can reject the null, okay? Anybody have any questions about that? Okay, so present the appropriately constructed label bivariate table, percentage table to test the hypothesis that race influences voting behavior. Okay, so what this is asking us to do is to take these raw frequencies in this crosstab and then convert these raw frequencies to percentages. So looking at this, how would I convert these to percentages?
You calculate vertically, right? So you would take like the 100 and divide it by 157, and then the 57 by 157 for the first column.
Good. Good, so why don't you go ahead and do that for me? So let's go say for whites. Yes. No. So that's correct. We calculate vertically, not horizontally. So for whites who said yes, they voted in the 92 presidential election, what is the percentage there? So you just do 100.
Sorry, I don't have my calculator. I am trying to pull it up on my computer.
So you would get about 64% there, right? So the answer to this first square is 64%. Now, I could do that in the sense that I could do 57 divided by 157, but I already know it's going to be 36% because the percentages should add up to 100%. Hopefully everybody remembers that. Now this next one, we're going to do 11 divided by 21. And we're going to get about 52%. And here, obviously, we'd have 48% here, okay? So now that we got that, we can do a comparison of the percentages here to determine whether or not race influences voting. So what it wants us to do at this point is use the percentage difference to describe the pattern of association in the above table. Okay. So looking at these percentages, does it appear that race influences whether or not people voted in the 92 presidential election? It seems like it does to me, right? In the sense that, there's about 12 percentage points difference between, whites and blacks, whether or not they voted in the 92 presidential election or not. So it does appear that there is a relationship between race and whether or not people voted in the 92 presidential election. It'll be interesting to see, if this still holds for the 2020 election, but, data's still out there, data's still being worked on at this point. All right. So let's go ahead and take a look at, this one is asking us to do the t-test. So saying that in 1991, the General Social Survey, so this data is pretty old, survey, respondents were asked how much confidence they had in different areas of American life. Executive branch of federal government, Supreme Court, Congress, military, major companies, banks, organized labor, education, medicine, and so on and so forth. Okay. Now this table below gives us the mean scores on the confidence index for those with less than a high school education and then those with a high school education or more. Okay. So what we have is we have two samples. We have a sample where we have people who didn't graduate from high school, and then we have a sample of people who graduated from high school and have high school diploma and higher. Okay. So this mean looks at their confidence in American social institutions, being described here. And this is the sample standard deviations here. These are the n, so the sample size for each group. Okay. So what it wants us to do for number 9, using correct statistical notation, state the research hypothesis and then the null hypothesis to test whether those with lower levels of education have significantly lower mean levels of confidence in American social institutions than those with higher levels of education. So having said that, how would we write, hopefully you all remember how to do this, and if you don't, this should be a good refresher. How would we go about writing the research and the null hypothesis if we were doing the t-test? How would we write the research and the null? We're going to start off the research hypothesis with H subscript 1, right? And the null hypothesis, would it be H subscript O? So where are we going from here? We have a 2-sample t-test. Where are we going from here? I mean, y'all can guess too, if you don't get it, just guess and we can see if it's the right answer.
I know it starts with M1.
Okay, so that's correct. So what we're going to start off is, it's actually mu. So it's kind of looks like an M and a U together. So it's mu1. And now we have a 2-sample t-test. So there should be some other stuff, right? What else do we need? Since we have 2 samples, we should have mu1 and then hopefully you specified 1 for, and we should have a mu2, okay? So good. Now what we also need to make sure is that so we can have less than, greater than, or not equal to here. So having said that, looking at this, what it's specifying here, it's saying we're going to test the hypothesis, test whether those with lower levels of education, so the first group are the people with lower levels of education, do they have significantly lower mean levels of confidence in American social institutions? So knowing that it's lower, should we have a less than? We should have less than, good. So we should have less than, because of the fact that we're saying that this group has lower levels of confidence in American social institutions than this group. If it had said this group has greater levels of confidence, we do greater than. And if it said that this group had, you know, a different, you know, level of confidence in, you know, American social institutions, and we would do not equal to. So it says lower than, so we're going to do the less than symbol. Now for the null hypothesis, we would write it somewhat similar, but instead of saying less than, we would say equal to. There's actually two ways to write this, and the textbook only tells you to say equal to, but you could do equal to, or you could do greater than or equal to, but the textbook doesn't talk about this. So when you're doing the exam, just understand that the null hypothesis is written as equal to, because for some reason the textbook doesn't really talk about that. So just, the textbook writes the exams too, so let's just go with what they say. So that's how you'd write the research, and then you'd right below, you'd write the null hypothesis, okay? Now, a t-test is appropriate for this research problem. Explain why. So can anybody tell me why the t-test is appropriate for this research problem, based on just what we know so far?
Because we're testing like two different samples or something like that.
Well, that is one reason why you would use a t-test, yes. There's a couple other reasons. That actually might be a little hard, so I'll just kind of explain it here. One, your dependent variable is interval ratio. So we have mean, so we have interval ratio level data. That's one thing. That's one of the assumptions of the t-test. And then two, we have a sample standard deviation, which means that we don't have the population standard deviation, so we wouldn't be using a z, we'd be using a t. So that's why we would be using the t-test. Okay, so good. Now, assuming the variances are equal, calculate the value of the t and the degrees of freedom for this test. Okay. Now, assuming that the variances are equal. So there's two ways. So you can calculate the t using this equation. So what you have to do for the top part of the t, you would take the mean of the first sample subtracted by the mean of the second sample. Mean of the first sample minus the mean of the second sample divided by the estimated standard error of the mean for two sample t-test. So let's do this part because this is going to be pretty easy. So the mean of the first sample is 2.0579. So that should be easy. 2.0579 minus the mean of the second sample, which is 2.1530. All right, now we're saying that the variances appear equal, which means that to get this bottom part, we're going to have to do this. Having said that, you're not going to have to do this on the exam. It would take too long, and I don't want to do that to you all. So having said that, that's going to take too long, and I don't want to do that to you all. Kind of don't want to do it right now either, because it's going to take too long for me to even do it right now. I'm not lazy, it's just that what's the point? So having said that, there's two, I'll give you all the option. I can either open up the answer key and I can show you what it would look like if you wanted to set it up, or we can just do it together. So I'll give you all the option. Do you want to do it together? Or do you want to just look at what the answer key, what it would look like? I'm okay with either one.
Answer key.
It look like.
The answer key.
Okay. All right, so we'll just open up the answer key. So if I were to put it together, what should it look like? So the top part is already done, okay? So then what you would do is if you remember from this, so the n of the first sample minus 1, okay, it would be the first part. Now we see that the n of the first sample is 154, so you do 154 minus 1 will give you 153, and you'd put it there. Now what you also have is, right next to that is the variance of the first sample, and you multiply it by that. Now, you don't have the variance, you have the standard deviation. What do we need to do to the standard deviation to get the variance? We square it up. So we take this 0.388 and we square it up. So we take 0.388 and we square it up. Okay, we put that there. Okay. Now the second part of the equation is very similar to the first part in the sense of like n of the second sample minus 1 times the variance of the second sample. So what you would do is you take the n of the second sample, which is 688 minus 1 will give you 687, times 3.64 squared. Okay. So you'd put that 3.64 squared times 687. Okay. Take those two numbers, you add them together. Now the bottom part of the equation is obviously the n of the first sample plus the n of the second sample minus 2. So we're going to take the n, 154 plus 688, which will give you 842 minus 2. So this number plus this number minus 2. Then you solve for that and then take the square root. Now, obviously, this part is the n of the first sample plus the n of the second sample divided by the n of the first sample times the n of the second sample. So you go ahead and take these, add them together. Then on the second part, on the bottom part, you multiply them together. Okay, take the square root of that, multiply those two numbers together, divide that into that, and then you would end up with a t which is equal to negative 2.9. So, but like I said, because of the fact that you don't need to do that on the exam, just don't even worry about it now, but that's how you would set it up. And if you follow the order of operations properly, you should get the right answer, which would be negative 2.9. Okay, so having said that, we'll take a look at number 11. So we calculate the t for a two-sample t-test. And then based upon the t, can the null hypothesis be rejected? And if so, with what degree of confidence? Or when it says with what degree of confidence, it means at what alpha levels? And if not, why? Why not? So how are we going to determine whether or not we can reject or fail to reject the null hypothesis? Okay. Now, do you all know where to start off here? How we would go about determining whether or not we can reject or fail to reject? Okay, so now we'd have to go into the go ahead.
Find the degrees of freedom.
Good, so we'd have to find the degrees of freedom. We know that the variances are equal. So what we do is we take the n of the first sample plus the n of the second. So we would have this equation n first sample plus the n of the second sample minus 2. So we have two restrictions, which are the two samples. Now, if I recall correctly, the n of the first sample is 154, so we take 154. N of the second sample is 688, so we do 154 plus 688. Then we subtract that, and we're going to get degrees of freedom, which is equal to 840. Now, hopefully you all remember that when your degrees of freedom is 840, what that means is that we're going to use this infinity symbol, because if you have degrees of freedom, which is 121 and above, we're going to use that infinity symbol. Okay. Now that we have our degrees of freedom, what other piece of information do we need? Well, we need to know our whether or not we're doing a one-tailed or a two-tailed test. So can anybody tell me, are we doing a one-tailed test or are we doing a two-tailed test based upon our original research hypothesis?
Two-tailed test. What?
Now, make sure you understand that there's a difference between a two-sample and a two-tailed. When you're doing a two-sample, you're pulling two samples, right? So here we have two samples. We have sample of people who have less than high school education, and we have a second sample of people who have high school or more. So that's two separate samples. So we have an N of 154 and an N of 688. Now, a two-tailed versus a one-tailed is not like a two-sample versus a one-sample. They're not related per se. A two-tailed versus a one-tailed test is actually about direction. If you specify direction, you'll have a one-tailed test. If you don't specify direction, you have a two-tailed. So thinking back to our original research hypothesis, did we specify direction there?
No.
Yes, we did.
Yeah.
Remember our research. Did somebody turn their phone off? Or
Sorry.
all right, so our original research, let's go. So our original research hypothesis was this, okay? So we said that the mu of the first sample was less than the mu of the second sample, right? Well, technically population mean. So we had a direction because we had a less than symbol. If we had either a less than or a greater than symbol, then we have direction, okay? Now, if we had this not equal to symbol, then we would be a two-tailed test. But because we have a less than symbol, we have a one-tailed test. Everybody with me when I'm talking about one-tailed versus a two-tailed test?
Yes.
One-tailed test is not the same as a one-sample test. You could have a two-sample test as we just had, that's also one-tailed, okay? Confusing, I know, and if you're wondering, yeah, this exam is tough. You probably figured that out when we covered chapter 8. Having said that, somebody took the exam already. They got a 98%. But if that person took the exam already, that person was really well prepared, obviously. So I don't think that that's going to be normal. Just understand that it's possible. So, you know, make sure you're on this stuff because it is a hard exam. But if you study hard, you get the results. Work hard, you know, you get the good results. Having said that, so we have a one sample test. So what we're going to do is we're going to come back over to this table, T-table. So we know we're having degrees of freedom, which is equal to infinity because we have, it's above 121. We have a one-tailed test. Let's just check it at the 0.05 alpha level. Our T critical is 1.645. Now we already established that our T obtained was a negative 2.0, was it negative 2.90? Negative 2.90. So our T obtained is negative 2.90. If we were to have actually calculated all that, it'd be negative 2.90. Now our T critical, which is the critical value that we need in order to reject at the 0.05 alpha level is 1.645. Okay, so based upon the T obtained that we got from actually calculating the T and then the T critical, the critical value that we need to reject the null hypothesis, based upon these two numbers, do we reject or do we fail to reject the null hypothesis in this situation? Do we reject or do we fail to reject? Okay, so we want our T obtained to be either, we reject, okay, good. Because we want our T obtained to be either at or above our T critical. So let's just say this is my hand, this hand is a T obtained, this hand is a T critical. We want it to be either at or above the T critical. If it's either at or above the T critical, then we reject. Now we can clearly see that our T obtained is above our T critical at the 0.05 alpha level, so we reject. Now let's just check it at the 0.01 alpha level. So at the 0.01 alpha level, our T critical is 2.326. So at 2.326, you know, obviously this number is higher than 2.326. So we would still reject the null hypothesis. And at the 0.001 alpha level, you don't see it on this T table, so you can't really tell, but I don't think that you can reject at that point. All right, so let's go ahead and like open up. So we would reject the null hypothesis. Good. All right. So I think this one is asking us to construct a confidence interval for both black females and white females. Now, I'm only going to do it for the black females because if you know how to do it for one group, you know how to do it for the others. It's the exact same process. So as long as you know the process, it's the same thing. So can anybody remind me what the confidence interval formula is? CI is equal to what? And we're talking about confidence intervals for means. You can do it for proportions as well, but I'm not sure if you need to do that for this upcoming exam. But you will need to do it for the means. So what's the confidence interval formula for means?
Is it CI equals the dash over the Y plus or minus Z?
Plus and minus Z, yeah. The Y with the line over it is the mean, correct? Z, and then there's something else. There's one more thing.
And then the
Time.
forgot what that's called. It's the like a little dashing O and then the Y. Is it
It's the standard error, correct, good. Okay, good. So we're gonna write the standard error of the mean. Okay, good. Now, most of the stuff we have up here already. So if you look at it for black females, I think that the mean was 40.158. So we can just put 41.158 here. Plus and minus. Now, what is the Z value for a 95% confidence level? So there's three traditional ones. You should probably memorize these before the exam. There's 90, 95, and 99. What are the corresponding Z values for all three of them? 90, 95, and 99.
Is it 98.6 or 96.8, something like that? For the 95? No, wait.
No. I mean, there's two numbers that are right, but that's not the right number. $96.8. You know where you got that number from? I think you're thinking about the standard human body temperature. Actually, maybe
95%
98.6.
is
Is what, man, Nika? I didn't hear that.
the 95% is it 1.96?
Good, so it's 1.96. So just remember that for 95% it's 1.96. For 90% it's 1.65, and then for 99 it's 2.58. Okay, so we have that. Now what we need to find is the standard error of the mean. Now, in order to calculate the standard error of the mean, what we need to do here is we need to find the standard deviation and the n. So when you find the standard error of the mean, you take the standard deviation, which is 15.246, divided by the square root of n, which is 76. So what you would do, once we get this, you're going to plug that here, and then we can solve. So what we're going to do is we're going to take 76, take the square root of 76. We're going to let's just say 8.72. Okay, so we're going to do 15.2, what is it, 246? 15.246 divided by, was it 8.72? All right, so 8.72, and then you would get 1.75. Let's go ahead and round that up to 1.75. So our standard error is 1.75. So we put 1.75 right here. All right, so now we just go ahead and we solve. So why don't you all go ahead and feed me these numbers? We have 1.75 times 1.96. What's that going to give me?
3.43.
Good, so we did 3.43. So we can construct our interval now. We're going to first find the upper bound. So we got the sample mean is 40.158. Then we go ahead and find the upper and the lower. So the upper, you would add 0.343. When you add 0.343 to 140.158, what do you get?
43.588.
So we go 43.59. And then when you subtract 3.43 into 40.158, you get what? The lower bound.
36.73.
Okay, so we go 36.73. So this is the lower bound, this is the upper bound. So when you're estimating the actual population parameter, you would say that the actual, we're 95% confident that the true population mean is not lower than 36.73 and not higher than 43.59. Okay, good. So that's how you go about calculating the confidence intervals. Now, like I said, if you want to, you can just go ahead and do it for white females on your own. It's the exact same process. Write out the formula, plug things in and stuff like that, and then it'll look good. Okay. All right, so next, oh, we already did this one. Will a 99% confidence interval give a more precise estimate of the mean occupational prestige score of each group? Explain why or why not. So would it give a more accurate or more precise, that is it tighter interval or is it wider?
Tighter, right?
Since I just said no, there's only one option left now, right? You have a 100% chance of getting this right, as long as you say the opposite answer. So it's going to be wider, okay? Now, why is it going to be wider? So obviously with a 99% confidence level, we're not going to be having 1.96 here. What number are we going to have here? What number are we going to have here?
Oh, 1.65.
No, that's for 90%. If we were doing 99%, what would we do? What number would we have here?
1.98.
What?
1.98.
It's 2.58. Okay.
2.58. Good. Okay, so we'd have 2.58. Good. So 2.58, right? So you did it reverse. With 2.58, if we had that here, and then we multiplied it by 1.75, we would get 4.515, which means that if you were to add that to 40.158, the interval would get higher this way. If you were to subtract 4.15 into 40.158, it would get lower. So your interval would get bigger. So the higher, essentially, in a way, the higher your confidence level, the bigger your interval gets. Why? Because you're more confident that the population parameter is going to fall within this interval. So if you shrink your confidence level, what happens is you have a more precise estimate though, right? So that's kind of the relationship between like a confidence level and a confidence interval. You want a higher level, your interval is going to be bigger and then vice versa. If you want a more precise estimate, your confidence level is going to go down. There's also a way to make your estimate more precise in the sense that you can make it more precise if you increase your sample size. So what will happen if you increase your sample size is that your standard error of the mean is going to be smaller, which will give you a more precise estimate. Okay, so you'd have a tighter interval. So those are just some of the things you probably want to go ahead and review that type of stuff before you take the exam as well. Anybody have any questions about how to calculate confidence intervals? All right. I think the rest of these are just kind of like questions, multiple choice stuff. Okay, so for 15, a left-tail test is one where the sample outcome is hypothesized to be what?
B.
Be at the left tail of the sample distribution. That's why it's called a left tail test, right? And of course, at that point, you're testing below the mean. Good. 16, when conducting a statistical hypothesis test, what is it that we are actually doing?
Whether the research hypothesis is true.
No, so what we're doing is, the reason why that's not the case, even though I think sometimes people think that that's the case, is when you're doing, when you write the research hypothesis, you write the research and then you write the null, right? But then what you do with the research hypothesis is you leave it alone, you don't touch it. And then the null hypothesis is what you test. So you have two options. You either reject the null or you fail to reject the null hypothesis, okay? So you don't really do anything with the research hypothesis. You just state it, and this is the opposite. Now, if you reject the null, you'll have support for your research hypothesis. But if you fail to reject, it doesn't necessarily mean that your research hypothesis is inaccurate. This means you have no evidence, you have no support for your research hypothesis. So when you're rejecting versus failing to reject the null, it's just important to understand that you're testing the null and your goal is to reject it and your goal is to falsify the null to provide support for your research hypothesis. But even if you fail to reject, that doesn't necessarily mean that your research hypothesis is wrong. It just means that there's no real evidence there for it. So the correct answer is that you are falsifying the null hypothesis. All right, 17, according to the central limit theorem, if the sample size is larger than 50, the sampling distribution of the mean is what?
Approximately normal.
Good, so it's approximately normal, good. What is the symbol for the standard error?
B. Wait.
B, so B, yeah, the answer is B. And then these two look exactly alike, but the difference is the line over the Y makes it the standard error. This is the population standard deviation. This is the estimated standard error. This is obviously the sample standard deviation. All right, the last one. The probability associated with obtaining a particular value of Z is referred to as its what? The probability associated.
P-value.
The p-value, right? So the p-value is the probability value. Good. All right, cool. So we have got through this review. So he said, if y'all have any questions, you can ask it right now, either about the review or anything else. Can y'all hear that train in the background? Oh, you can't hear it? Okay.
Where is that at?
Just around me. Somewhere back here. I don't know. All right, anyway, so nobody has any questions, so you all are just gonna ace this with not a single question about this stuff? All right, cool. So I mean, if you don't have any questions, I'll go ahead and stop the recording.